if you have an equation to deal with that has, let's say, a bit more of a logarithmic problem to deal with, all we have to do there is just try and get things nice and organized and then reuse exponents. So if we have something with multiple logarithms in it, what we're going to start by trying to do is get them onto either side. That is, we want to express the equation in the form log base b of m equals log base b of n. Then use the one-to-one property to rewrite the equation without logarithms. That is, note that you can just talk in terms of the values inside of them if you have the same base, solve for what's left, and check to make sure that your solution actually works. So, if you want to take an example with this process and solve the natural logarithm of x minus 3 equals the natural logarithm of 7x minus 23 minus natural logarithm of x plus 1. Essentially, our idea here is to use that nice exponentials case from earlier, use that same sort of logic in terms of one-to-one things to remove the parts that are inconvenient. Where here, what we have is the natural log of x minus 3 equals the natural log of 7x minus 23 minus the natural log of x plus 1. So we're going to take these two, use the quotient rule, and bring them together as the natural log of 7x minus 23 over x plus 21. And then we'll recognize that just like when we had two exponents of the same base on either side, the exponents kind of cancel each other out and we really need to focus on what we're raising them to. We do the same thing here with these logarithms. That really all that's changing is the stuff inside of the logarithms because the actual logarithms themselves are the same. So if we want to make these two sides equal, really what we need to do is find out when x minus 3 is equal to 7x minus 23 over x plus 1. Fix that, I smudged it a little bit. So we're left here with a not quite basic, but at the very least approachable, more comfortable rational equation to solve. Where, again, we need to be careful of things with domains in this case, that we don't want this to be -1, but we also didn't want it to be -1 over there, so it actually didn't add any more problems. And then from this point, if we want to actually solve this, it's a lot of multiplication, some subtraction, and then factoring. What we're going to do is multiply over that x plus 1. So we'd have x minus 3 times x plus 1 is equal to 7x minus 23. And I'm really weirdly aligned on the left, but that's okay, we'll work with that. Then from here, multiply this thing out with a parenthesis there like it's supposed to be, and what we would end up with is x squared minus 2x minus 3 is equal to 7x minus 23. Keep getting those 2's and 3's backwards, it's silly. And then pull all these things apart so you get with a quadratic equation that has this side equal to 0. So we're going to subtract over the 7x, add over the 23, and what we will get is x squared minus 9x plus 20 is equal to 0. And with this, hopefully you can tell it factors into x equals 4, x equals 5, that we have our potential solutions in that form, because 4 times 5 gets you 20, -4 plus -5 gets you -9, so our answers there potentially are 4 and 5. But from there, we do need to check that both of these work. So just off to the side here, I'm going to run through each of them, that if we take at 4, starting from the top, we don't need to start from the top, we could start from here if we wanted to as well, but I'll start from the top just because it's where we were. We'd have the natural logarithm of 4 minus 3 is equal to the natural logarithm of 7 times 4 minus 23 minus the natural logarithm of 4 plus 1. On this side, we end up with the natural logarithm of 1, which I'm going to leave as the natural logarithm of 1 for a second, even though hopefully we know what that's supposed to be. But on the other side here, we're going to have the natural logarithm of 5 minus the natural logarithm of 5, where even though we generally wouldn't write this kind of thing as the natural logarithm of 1, it is the same because, as we should know, the natural logarithm of 1 is equal to 0, and log 5 minus log 5 is also equal to 0. If I wanted to write that as natural log of 1 equals natural log of 1, I could, but that's the point. The point is we're killing everything, so that one's good. Lots of death. Hooray. On the other hand, for the natural log of 5 minus 3, what we get if we plug in x equals 5, for this, on the other side, we would have the natural logarithm of 5, or excuse me, not 5, it should be a 7 there. 7 times 5 minus 23 minus the natural logarithm of 5 plus 1. Yeah, that's right. The other way you could write this is in terms of bringing those together, you'd have 5 over 5, you get log of 1, but yeah, whatever. It's brainstorming as I'm writing. We'll get there. Anyway, over here, we would have the natural logarithm of 2, which is not as nice as the natural logarithm of 1, but it's still just a number, so we're going to leave that as it is. And on this side, we would have 35 minus 12 is the natural log, or 35 minus 23, excuse me, is the natural log of 12. And then over here, we have minus the natural log of 6. And we can pull this apart however we want to in order to make it make the most sense. But to me, what makes the most sense is using the quotient rule here, which you could have done there as well. And you would take the natural log of 12 over 6, or the natural log of 2. So sometimes it's not entirely obvious that these things are going to work. If you have these solutions, they should work. The only issue might be if you end up with something negative, but in this case, we're positive all the way through, so we're good. Both of these are fine, and we get that our solution set at the end is both of 4 and 5. And we're going to finish the section here with some applications working through these kind of processes in terms of some more real-world context.